Titrations. So today you guys are going to be the lab quest. You guys are going to be calculating pHs of different increments after different increments of base has been added in titration in order to form a titration curve. And part of what you have to get out of today is knowing the characteristics of different kinds of titration curves. By the end of it, you should be able to look at a curve and go, I know in the burette is a strong base, I know it's a weak acid being titrated, and I know that based on where the equivalence point is, I know it's a strong acid, I know it's a weak base, whatever. You're going to be able to tell all about the curves just by what we're doing today. So today we're going to do this. Tonight you're going to let it mill in your head since it's no homework night, and tomorrow we're going to do an activity about this. So you'll have a couple days to let it all sink in. So the first titration we're going to work on is the titration of a strong base and a strong acid. This is what I term strong titration. When I say strong, that's what I am referring to. Strong, the strength of the acid and base. I'm using maraschino red today for Valentine's Day. Happy Valentine's Day, or to those of you who are single, like I am, happy Black Tuesday. Hope you're enjoying it, enjoying your day. When we start with our titrations, every single addition is an invasion. So we're going to have multiple invader problems that we're going to be calculating over and over. But you know, when you do a titration, you always hit the keep button before you added anything from the burette. So getting the initial pH of whatever's in that little beaker is what we have to do first. So here we're going to calculate the pH of that acid before the addition of any base. So how do I find the pH of a 0.8 molar HCl? What do I do? Negative log of our H plus concentration, which is 0.8. So if I take the negative log of 0.8, what do I get? At 0 mils added, we have 0.097 is equal to our pH. Does everybody agree with that? I want to make sure it's right for the video. Okay. All right. So now we're going to do our first little calculation. These in a strong are going to be easy because if you think about what the invasion equation is, we're adding base to a burette that has H plus in it. What's the product of that reaction? H2O. So we really never are concerned with what's being formed in these. We're only going to look at our mole ratios of our reactants. So we're adding 20 mils of base. 20 mils of base at a 0.6 molar. What's 0.02 times 0.6 to give us moles? Like with any invasion problem, we do moles. Is that correct? Everyone agree? 0.012. Now, our H plus concentration in our beaker or in our Erlenmeyer is not going to change. Whatever we get now for this acid, we use the same every single time, right? Because we never change what's in the beaker in the titration. We only just keep adding base to it. So 0.04 times 0.8 is, so we're going to have 0.032 moles of acid all the way through the titration. So we're going to lose how many moles? 0.012. And I don't care about forming water, so I'm not even going to mess with that. So I have no base left over at this point, so the invasion was a fail, and we get 0.02 moles of acid. So how do I find the pH? I have to take that 0.02 moles and do what to it? Take the negative log? No, got to convert it to molarity. So I do my total volume. It was 40 mils of acid. It's going to stay 40, but we added 20 mils of base to it, so that's 60 mils or 0.06 liters. My concentration of H plus is 0.333 repeating. And so my pH is give me 3 decimals. Let's just be consistent. 0.477, and this was after 20 mils of the base. And I'm just writing it like this because we're going to be plotting mils of base added with pH at the end of this, and it's just going to make it easier for us to find if we do it that way. Okay. After 20 mils of base, we have a pH of 0.477. Feeling good? All right, let's keep titrating. Now we're going to add 20 more mils of base. Dump a whole bunch in there. That's a lot. That's almost the whole burette, isn't it? It's a lot. We're actually going past 50. So we're going to pretend that actually didn't happen in a real titration. But 40 mils of base, 0.04 times, what was it, 0.2 our concentration, or 0.6? 0.6 times 0.04 is 0.024. We're adding it to our same amount. And you're going to have to remind me because I did this last period and my numbers are all over the place. Point what? 0.032. So we're going to lose 0.024, lose 0.032. Oh, yeah. No, gosh, guys. Demo needs to not be here today. We don't lose different amounts, Demo. Minus 0.024. Gain 0.024, which we don't care about. And so we get 0.008. All right, so we take the 0.008 moles divided by the total volume of 80.08. So what is my concentration of H+? It's 0.1. 0.1 is a pretty easy pH to know. So we have a pH of 1.000, and this was after the addition of 40 mils of base. All right, we're going to keep adding in the titration, and we're going to add 53 mils of base. So my OH concentration is 0.053, number of moles I mean, is 0.053 times 0.6, and what is our moles of base? 0.0318, plus our stayed constant 0.032, right? Okay, and we're going to have none of this. And what are we going to have here? 0.0002. All right, so our pH, hoping to see a change here. Big change. What am I? 0.0002. Like that? 0.0002 divided by our total volume is 83 mils, 93 mils. 93 mils, right? 0.093 liters. So my concentration here of H+ is 0.00215, giving me a pH of 2.666. Dodged a bullet there. And that's after the addition of 53. So we're still, think about how much we've added. We're still saying pretty gosh darn low, aren't we? All right. So what we're going to have to get to next, because if you look, you see how we're getting close to running out of acid here? Okay. The next point we're going to calculate is figure out how many mils of base we'd actually need to reach the equivalence point. Does anybody remember the definition of the equivalence point? Equal, not concentration. Think about that Stoic table. What do you think the equivalence point would be? When moles of the acid and moles of the base are equal. That is truly the definition of equivalence point. And in a strong titration, it's going to lead to seeing something happening that's going to be pretty, makes a lot of sense. So if we have 0.032, is it 0.032? 0.032 moles of the acid, we would then need 0.032 moles of the base to be at the equivalence point. With our molarity being, of the base being 0.6, and our moles that we need is 0.032, how many liters would we have to titrate? .0533. Well, from a burette, it would be better for me to say this is what? This volume. From a burette. Yeah, 53.3 mils. So I need 53.3 mils to reach the equivalence point. And that's my answer to this. The next thing it says, and I'm just going to continue up here, calculate the pH at the equivalence point. Is there really anything to calculate? Because look, minus 0.032, minus 0.032. Yeah, we make 0.032 moles of water. What do you think our pH is? 7. Yeah, we're at a pH of 7, and it is only in this strong format that we'll have a pH of 7. As this stuff is going on, guys, I'm going to keep talking because I'm on video. All right, are we good with this? Do we understand this? When we get to the equivalence point of a weak strong, we're not going to be in the same situation. It's not going to be at 7. You're actually going to get to see why. All right, so now to finish up the titration, we're going to go 5 mils past the equivalence point. So we're going to have 53.3 plus 5 mils, so that's 58.3. So 0.0583 times 0.6. What do we get? Anybody? Can I get a second on that? All right, H plus then is going to stay what it always is, 0.032. So we're going to lose 0.032, lose 0.032. This time our acid ran out. And so we have 0.0298, 0.00, yes. I'm good with the OOs today. Moles of your base. So how do I find the pH of moles of base? I take moles of base. What do I divide by? Total volume. So I was at 58.3 plus 40. So what is that? 98.3? So divided by 0.0983. We good with that? All right, and so my OH concentration is equal to what? 0.0303. When I take the negative log of this, it gives me POH. And then my pH is, all right. So now we're starting to see the finish line of this. This was at 50, what was it? 58.3 mils of base added. All right, so what we're going to do, I have a little grid here. You don't have that in your notes, but you can kind of sketch it. It doesn't need to be exact. But what we're going to do is we're going to take all the points we just figured out, and we're going to put pH on the Y like every other pH titration we've done, and mils of base added. Is there something wrong? There's whispering. Is there something wrong with my numbers? Where did I get anything? You guys gave it to me. Where did I get what? That was the original 40 mils plus. We added 5 past the equivalence point. Oh, this is just the 40 plus the 53. Please tell me we're right with our numbers. Do not freak me out because I'm going to have to redo this video. Okay, so let's go ahead and start plotting. You guys have the ordered pairs in front of you. It's easier for you. So before the pH, I guess I'm just going to do increments of 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And mils I'll do, each line is 5, 10, 20, 30, 40, 40 and 50, 60. Okay, so before we added any base, what was our pH? Y'all have to jump back because you have to look back as well. Come on. So it's almost 0.1, so way the heck down here. Okay, and then we added 20 mils, and what was our pH? So about a half a pH unit. And then did we go to 40? And what did that come out to be? 1. So yeah, we're barely moving here at all. And that's very indicative of a strong. Flat, 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 flat. And then we get to, what did we do, 53 next? And what was that? Okay, we're starting to see something happening here. And then we went to 53.3, which is barely different than this 53, and that was our equivalence point of 7. That is a sharp rise, okay? And then after that, we went 5 mils past that, and that was at 12, 12.5. And I didn't do any more points, but it would continue then to slowly flatten out. So we start out super extreme. That's the first telltale sign you have a strong titration. It'll be extremely low or an extremely high pH depending upon what's in your beaker. Because we could have a base in the beaker and be titrating with an acid, and the curve could go the opposite direction. So we're going here, 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 and then we have this super sharp rise, and then we'll start to see it flatten out. All right? This is how we 100% know that we have a strong titration. The rise is super duper sharp, and the center of that rise is where? An equivalence point of 7. Okay? That's how we know that this is a strong titration. That is not a very pretty curve I drew, but you get the idea. Okay? All right, now let's get really into some work, and we're going to do the calculations for a weak strong titration. All right, a titration is performed by adding 0.2 molar NaOH to 24 mils of hypochlorous acid. The Ka of hypochlorous acid is 3.5 times 10 to the negative 8. So, weak acid is in the beaker. The 24 mils of it stays the same, and we're just going to add strong base to it. So we want to know the pH of this acid before we add any base. So how do we find the pH of HOCl? Right, well, how do we find the pH of HOCl? It's a weak acid. What do? Add it to water and do what? Have we forgot how to find the pH of a weak acid? How do we find the pH of a weak acid? Add water to it and put it in what? A rice table. Why are y'all acting so weird? It's not a hard question. How do we find the pH of a weak acid? Add water and put it in a rice table. HOCl plus water. This is going to make for a really long class if we're going to be this quiet. OCl minus plus H3O plus. Our original concentration, we know. It doesn't matter how much we have of it. It is 0.35 molar. 0, 0. And those of you who know how to do this, go ahead of me and get these numbers. 0.35 minus X. I'm going to trump that. X and X. So my H plus times OCl minus divided by HOCl is equal to my Ka. So I get X squared over 0.35 is equal to 3.5 times 10 to the negative 8. My X then, which is equal to my H plus concentration, is 1.107 E negative 4. So my pH then is, we have 3. So I'm going to just say 3.96. 3.96. Is that what we got? I'm seeing faces again back there. Yeah. Not without showing this. Yeah, you can. So are these numbers correct? So our pH then, this was after the addition of 0 mils of base. We had a pH of 3.96. Can anyone see a difference already in the curve? Do you see how we're not as extreme in pH starting? Okay. And so now we're going to go ahead and calculate the pH after the addition of 5 mils of the base. All right. This is an invasion. We're invading with OH minus into HOCl. This is going to have a single-headed arrow. Ugh, I'm not happy with my writing today. An invasion has a single-headed arrow, and we're going to make OCl minus plus H2O. So our moles of acid will not change. We have 0.005, oh, no, space. For acid, we've got 0.024 times 0.350 molar. So how many moles of acid are we going to have all day? 0.0084. We've got to remember that number. This time we have a base that is 0.2 molar, and we have 0.005 mils. So it's 0.005 times 2. 0.001. We have 0 of this. We don't care about the water. So we're going to lose. Is it? It's 0.2. It's not 2? It's 0.2 molar for sure? Okay. So 0.001 minus 0.001 plus 0.001. So we get 0 here. We get 0.0074 here, and we get 0.001 here. So what kind of system do we have left over after the invasion? Buffer system. So we can use Henderson-Hasselbalch straight up. pH is equal to the negative log of 3.5 times 10 to the negative 8 plus the log. You guys are just going to have to accept we're putting moles in here. Are you good with that? Do not want to have to do volumes every single time. We'll never get done. So it's the moles, aka molarity, of the ion over the acid. 0.001 goes on top because the ion's on top. So at 5 mils of base, what is our pH? Did you see what happened there? 6.5? It's close to being neutral, but we added 5 mils and it went up 3 pH units, right? So that's very different than what we saw before. What was it again? 6 point what? So 6.59. So after 5 mils of base, we're at a pH of 6.59. We didn't get here until we added 53 mils last time, right? All right, so let's go ahead and continue. I got to remember 0.0084. Calculate the pH of after the addition of 15 mils of base. So OH minus plus HOCl gives you. Do you care if are you cool with me leaving off the water? All right. So here we have 0.0084 moles of acid always and forever. We have 0.2 times 0.015, 0.003, none of this. Water's there, but we're going to ignore it. Minus 0.003, minus 0.003 moles. That's going to give us 0. This is 0.0054 moles plus 0.003 I forgot to do, and this is 0.003 moles. So what do we have left over? Buffer again. pH is equal to the negative log of 3.5 times 10 to the negative 8 plus the log of 0.003 ion over 0.0054. And again, I'm not doing molarity because if I did, I'd divide both of those by the same volume, leaving the ratio the same. So we can use moles in this case only. So what is our pH? 7.20 is equal to the pH, and that is after the addition of 15 mils of base. So you can see we're already past 7, and we're really not near the equivalence point yet. Okay, let's keep this going. Calculate the pH after the addition of 25 mils of the base. So we're going to go ahead and have OH minus plus HOCl gives us OCl minus. This is 0.0084, always and forever. So we're going to have 0.025 times 0.2, 0.005. 0. We're going to lose 0.005. We're going to lose 0.005, and we're going to gain 0.005. So none of that. This is 0.0034, and this is 0.005. Another buffer. pH is equal to the negative log of 3.5 times 10 to the negative 8 plus the log of ion of 0.005 over the acid 0.0034. 7.62 is equal to the pH after the addition of 25 mils. It's slowly rising. Yeah, and that's what buffering regions, you're going to see on the graph, it's a buffering region. Okay. Now it's probably time to start figuring out the equivalence point, I imagine. Nope, not yet. Of course not yet. Sorry, we're doing good on time. Addition of 35 mils of base. Oh my gosh, that's not what we're doing. So this is 0.0084. 0.035 times 0.2. 0.007. And this is 0. So minus 0.007 minus 0.007 plus 0.007. And so this is 0.0014. This is 0.007. Is that right? So what do we have left over? Buffer pH is equal to the negative log of 3.5 times 10 to the negative 8 plus the log of ion over acid. So our pH after 35 mils, 8.1. Still rising, right? Pretty steadily. So I'm hoping to see we need some sort of inflection to get to the equivalence point. We gotta have something that's going to show that. So we're going to go ahead here and just actually calculate the volume of base needed to get to the equivalence point. Our volume of base will be based on the 0.2 molar is equal to have our moles the same, it would be the same as that 0.0084 moles of acid, right? So how many liters would that be? .042 liters. Is it 420? Okay. So the mils would then be 42.0 mils. So that's what we're going to now use to calculate our equivalence point. So we have OH minus plus HOCl. HOCl makes OCl minus. I'm going to put water in here just because this time. So we have 0.0084 and 0.0084 and 0. We lose 0.0084, so this is the equivalence point. Our moles of our acid equal moles of our base, correct? But in the process, what do we make? We make that conjugate base. So we can't have a pH of 7 here because of this guy. This guy is going to give us a pH. Is this pH going to be basic? It's a conjugate base, so the pH is probably going to be basic, right? Which makes sense because we're reacting a strong base and a weak acid. If we have a strong base and weak acid titration, the pH of the equivalence point will be above 7. All right, so what kind of problem is left over? What do we have to do? This is a salt hydrolysis problem. So we need to convert this moles to what? Molarity. What is our total volume? It was 42 plus 24, 66. So that is 0.066 liters. So our concentration of OCl minus is 0.127 moles per liter. So how do I start a hydrolysis problem? What do I add the OCl minus to? Water. OCl minus plus water. Now I'm back in the world of equilibrium. Makes Hakel plus OH minus. We have 0.127, 0, minus X, plus X, plus X, 0.127 minus X, X, and X. So this type of equation needs a KB because it's HOCl times OH minus divided by OCl minus. So we only have a Ka, so we got to convert that by dividing 1e negative 14 by 3.5 times 10 to the negative 8, and that's equal to x squared over 0.127, trump the x. So Henderson-Hasselbalch's a lot easier than this, isn't it? Finding the pH of a buffer. I know. X then is equal to our OH minus concentration, which is 1.90 times 10 to the negative 4 moles per liter, correct? POH then, 3.72. What is pH then? We have an equivalence point of 10.28. How many mils was that again? 42 of base? So pH of 10.28 after 42 mils of base have been added. So our equivalence point is basic, indicating in your head you should be, oh, that means it's a strong base, weak acid titration. All right, our last point, yes. 5 mils past the equivalence point. Okay, so we have OH minus plus HOCl gives us OCl minus plus water. Our moles of this is still 0.0084. So we add 42 plus 5 is 47. So 0.2 times 0.047. 0.094? Yeah. So minus 0.0094 minus 0.084. Our base loses this time. Our acid loses this time, and our base wins 0.0084. We ran out of acid. 0.001 of this left over and 0.0084 of this left over. But what kind of problem is this now? Strong winds. I don't care what else is left over. We're only going to find the pH from that moles of base. So our moles of base, 0.001. We had 66 mils at the equivalence point. We went 5 past that, right? So isn't that 71? 0.071 moles divided by liters. This gives me the concentration of OH minus to be 0.014. My POH is, I heard 1.5 and 8.5, which is it? 1.85. What is pH? 12.15. So, at 47 mils past the equivalence, 5 mils past the equivalence point, we had a pH of 12.15. All right, good job. Let's plot that, and we'll talk about the differences. Okay, okie dokie. I want to try to be a little more deliberate on this one because there's something I want to do with it. 2, 4, 6, 8, 10, 12, 6, 8, 33. I can't do that, so we're just going to stick to 5. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. God dang it. 55, 60, 65, 70. And then that's mils of base. This is going to be our pH. So we'll just stick with 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, and 13. Okay, again, this is mils of base added in our titration. Starting out, what was our pH prior to adding any base? It was almost 3, right? Almost 4, 3.96. Okay, then we added 5 mils. What was it? 6.59? Okay. And then what did we add? We added 15, and that was 7.2. Okay, then we added 25, and that was a little bit past half. Okay, and then we added 35, and that was 8.15. Okay, and then we added 42, and that was the equivalence point. All right, and then we added, and then it'll flatten out. Okay, so this is also pretty indicative of what this looks like. So we're going to carry this through, and it's going to see right here is where the sharp rise is in this case. It's not a sharp rise, but it's still a point of high inflection in this particular curve, right? Do you see how this is pretty much the highest slope of anywhere other than here? So in the middle of this rise is where we'll find our equivalence point. We can see that that is not at 7, okay? Do you see, I know it seemed like this was changing pH a lot, but in the grand scheme of mils that we added, do you see how this stayed pretty flat? This is our buffering region. What calculation did we do over and over and over again? Henderson-Hasselbalch, right? This is our buffering region. So that is actually flatter than it might have seemed when we were doing the calcs. Because if we're using the same base in a weak and a strong titration with weak and strong acid, at the end we're going to end up at the same pH. Why? Strong will win, and we're going to use up all the acids, so the only thing that will be contributing to the pH is that base. Okay, so at the very end we should end up the same. And again, notice here we didn't start out quite as drastic as extreme. Okay, so that's one of the things. I do want to ask a question. I'm going to make a connection now. What if I were to say, hey folks, without knowing the Ka, pretend you didn't know it, what if I wanted you to find the Ka of the acid using the graph? This is the sexiest thing ever. It goes back to the last lab we did. It's the last lab we did. We can use Henderson-Hasselbalch, but it has to do with what we did in the last lab. What were we calculating? It's where the pH is equal to the pKa. Where does pH equal to the pKa? We call it at the half equivalence point, or we call it the midpoint. Now you're actually going to see what that is on this graph. That means half of the Haeckel was turned into Ockel, right? So we have equal Haeckel and Ockel at the midpoint or the half equivalence point. So to find them on your chart, we know our equivalence point was at 42 mils, right? Where would half of that be? 21 mils. So I'm going to go to 21 mils. What's the pH about at that 21 mil? It looks like 7.5 to me. Somebody Do 10 to the negative 7.5 and see if we get close to our K. That's pretty fantastic. Look how close we got just with my crappy graph. Okay? So that's how we use the graph to find the K, by going to that half equivalence point. At the half equivalence point, this is true. pH is equal to pKa. So if we know the pH at the half equivalence point, we can figure out the K. Got it? Midpoint or half equivalence point does not exist in a strong-strong because there is no conjugate we're making and there is no Hockel and Ockel cancel and all that stuff. So it only exists in a weak strong relationship like this. Okay, the very last thing we're going to do is just to restate, this is not hard, the things we already know. What are three major differences between titration curves in 12 and 13? Let's talk about strong-strong first. What are some indicators? Extreme beginnings, extreme start pHs. What else? Equivalence point at 7. And then that's my sound for sharp rise. Steep, sharp rise. Okay, so weak strong then will not have, not extreme, not as extreme start pH. Your equivalence point is not equal to 7, and you have a slower, less steep rise. You still find the equivalence point the same way, though. The center of whatever their steep rise is, even if it's not very steep, is still going to be your equivalence point. So let this stuff marinate. No homework tonight, obviously, because it's no homework night. Tomorrow I'm going to ask you at the beginning, review this one more time, and we're going to do an activity. And hopefully you'll enjoy the activity because I wrote it. So how about that?